Okay, we're beginning chapter 9, and we're going to start off with some infinite series. You should have learned these in pre-calculus. This right here would be what's called an infinite series because we have a set of numbers and it goes on forever. So you notice the dot dot dot. Now we also consider sums of these infinite series, so notice the summation notation. And over here we've got the upper limit here, infinity. N is what's called the index. 1 is our lower limit. The lower limit tells us where to start counting, and these are integers. And a sub n, which is found over here, would be what's called the general nth term, or the pattern that we're looking for in our infinite series. Now, sums of your infinite series may either converge or diverge. I want us to first consider some special series. The first one, 1/2 plus 1/4 plus 1/8 plus 1/16 plus so on, going on forever and ever and ever. What do you think about this series? Does it converge or diverge? And then 1 minus 1 plus 1 minus 1 plus 1 minus, and again so on. Does this add up to something? So this first one, a ruler or a stick or a length of something, 1/2 of that would be this. And what's remaining? Half. Then I'm going to add 1/4, which is half of that half that is remaining. 1/8 is half of the fourth that is remaining. Then 1/16 is half of that, and so on. And you can see that I could keep taking half of something. But what will this add up to equal? Does it go to infinity? Well, you can see that if we keep adding and adding and adding, we have simply one of these units. So this happens to converge. How about 1 minus 1 plus 1 minus 1? Some of you guys might be thinking, well, it's either 1 or 0, depending on where you stop. But remember, it's an infinite series, so it doesn't stop. So this one, the sum does not exist. It simply diverges. Doesn't add up to go to infinity. It just diverges. Now there's one last one that I want to talk about, which we will not completely resolve today. And it's this one. It's very similar to the one we have above, 1/2 plus 1/4 plus 1/8, but it's 1/2, 1/3, 1/4, 1/5, and so on. Do you think this converges or diverges? And I'm actually going to leave that with you guys as an open question. We'll talk more about that later. Okay, here we have the definition. If you have a limit s as n approaches infinity, then we say it converges, otherwise it diverges. Very similar to our terminology that we used in our previous chapter. Second thing I would like us to do is practice finding those general nth terms. So a sub n. And I'm going to give you a series of numbers, and I want you to think about the pattern. So this is now some problem solving. I want you to find the pattern and what will come in this box. So to kind of help you along, let's identify the first term as a sub 1, second one is a sub 2, a sub 3, a sub 4, and so on, and I want to know a sub n. So in a way, you're going to have to use the index 1, 2, 3, 4 to help. So let's see, these all have fractions, or actually I can write this as 1 over 1. So they all have fractions, so the numerator is 1. And your denominator, how do you get the denominator? 1, 4, 9, 16. Well, those are perfect squares of this index down here. So it's going to be n squared. Now we can represent the sum of this series as the sum from n equals 1 to infinity of 1 over n squared. Now I'm going to use n equals 1 because this happened to start with a 1 here. However, I hope some of you guys can take this extra piece here and recognize that I could also start at n equals to 0, but I would have to say my general nth term would be 1 over n plus 1 quantity squared. So take a look at that and see if that makes sense to you. Now let's try another series. How about 1 plus 1 plus 1/2 plus 1/6 plus 1 over 24 plus 1 over 120 and so on. What would the nth term be? Might help for us to write these all as fractions, and then you can tell that your numerator is always going to be 1. Now how do you get the denominator? We could also think of this as 1, 1 times 2, 1 times 2 times 3, 1 times 2 times 3 times 4, and so on. That's going to be a factorial. This is actually 5 factorial, 4 factorial, 3 factorial, 2 factorial, 1 factorial. Uh-oh, wait a minute, what happens here? Actually, by definition, 0 factorial equals to 1. You should remember that, so it actually does fit the pattern. So underneath here on our general nth term, we're going to have n minus 1 factorial. So that our summation notation can start with 1, and we end up with this. 1 minus 1/3 plus 1/5 minus 1/7 plus 1/9 minus 1 over 11, and so on. What is the nth term? Well, once again, I have my numerator as a 1, but sometimes it's positive and sometimes it's negative. This is what's called an alternating series. Alternating because it goes back and forth from positive to negative. So in this case, I'm actually going to start out with a little bit of my summation notation. I'm going to say n starts at 1, so I have my first term, second term, third term, fourth term. So all of the even numbered terms are negative. That means I have to have negative 1 to the n plus 1 power. When I plug in n equals to 1, I get an even exponent, which means I get a positive number. When I plug in n equals to 2, for example, for my second term, I get an odd exponent, which means I have a negative term. Now our denominator, how do we get 3, 5, 1, 3, 5, 7, 9, 11? Those are all odd numbers. You should know the pattern for odd numbers. It's either 2n plus 1 or 2n minus 1. And in this case, in order to start out with a denominator of 1, we have n equals to 1. And check it with the 1, 2, 3, 4, 5, 6th term. This is a sub 6. When I plug in 6, I have 2 times 6 minus 1. It works out for us. Now we're going to switch gears and focus on geometric series. A geometric series is one that has a common ratio or a common multiplier, and we usually call that r, and it has some first term a. So you notice a times r squared, a times r cubed, and so on. This series will converge only when your common ratio or multiplier has an absolute value less than 1, so we want the numbers to be getting smaller. This right here is a summation notation for a geometric series. The sum formula is also given to be a over 1 minus r. Okay, we're going to do a couple things with these geometric series today. So our next example, we're going to write the decimal that I'm going to give you as a geometric series and find its sum as a fraction. So 0.1 repeating. Now this is 0.111111, on and on and on. I'm going to have us rewrite this a little bit and look at this sum a little bit differently. Notice if I keep on adding these by putting a 0 in front of it every time, I'm going to have 0.11111. So this tells me that my first term, which is a, is 0.1, or I can write it out as 1/10. And my multiplier, what am I multiplying every time? My decimal is moving over one space to the left, or I'm multiplying by 0.1 or 1/10. This r value, and it's going to converge to a over 1 minus r, or 1/10 over 1 minus 1/10, or 1/10 over 9/10, which is 1/9. Now how can I write this out in terms of a geometric series? Well, I have a and I have r, and that's going to be enough. This is going to be n equals 1 to infinity, a times r to the n minus 1 power. Let's take a look at one more. 0.123 repeating. Let's try to figure out what the first term should be and what our common multiplier is going to be. Because for that to repeat, we have to have 3 zeros every time and then a 1, 2, 3. So that means our first term is 123 over 1,000, and our common multiplier is 1 over 1,000 to move the decimal place over 3 times. So I'm going to lead this time with the series and summation notation. This is going to be a times r to the n minus 1 power. All you do is plug it in. Now this is going to equal to a over 1 minus r in terms of calculating the sum. So that's 123 over 1,000 over 1 minus 1 over 1,000. So we can simplify this, and we end up with 41 over 333. Okay, we've got one last thing, and it's a different kind of question. This is actually a little bit different. I want to find the function represented by the series. This actually means find the sum. And interval of convergence, that means the r. What does r have to be? Now previously we had said that in a geometric series the absolute value of r has to be less than 1. So I want to figure out what that r, that multiplier, is going to be. The first term here is 4x over 3. What's the second term when n equals to 2? It's 4x over 3 squared. What about when n equals to 3? 4x over 3 cubed. And so on. So r equals to 4x over 3. In order for this to converge, the absolute value of r must be less than 1. So I need to solve this little absolute value equation. So 4x minus 3 must be between 1 and negative 1. Multiply everything by 3, and then divide everything by 4. So x has to be some number between negative 3/4 and 3/4. The second thing that we're asked is to find its sum. Well, the sum of a geometric series is a over 1 minus r. So I'm going to find my first term. How do you get the first term? Look at your lower limit, plug in that number, which is 1. So we'll have 4x over 3. Okay, so our first term is 4x over 3. Our common multiplier is also 4x over 3. So I'm going to simplify this a little bit. I'm going to multiply top and bottom by 3 so that I get 4x over 3 minus 4x. And this is an expression representing the sum.